my name is Tony. Problems, Universal Technology, Białystok, this is a city in the northeast part of Poland, near the border with Belarus, Lithuania. Those Universal Technology is one big university in Poland. We have about 7, 8 students. We have 6 faculties. Of course, the best one is Faculty of Computer Science. And the faculty have about 1,200 students. We have economic studies, the first degree. We have computer science, science of econometrics, and applied mathematics. And the same science and applied. I think it's all about our university. Let's do some presentation. I would like to say a few words about the artificial immune systems. First, I would like to say a few words about the biological human nature immune system. And next, about some words about artificial immune system, especially about one of them. Because in the domain of artificial immune system, there are developed technologies. I will focus on the negative space selection algorithm. Next, applications of negative selection algorithms when kind patterns with then we reduce those algorithms in the cybersecurity, but not only. And I will present some results with some algorithms used by some algorithms. And let's start with the architecture of later immune system. This system is very difficult. It can be compared only with the nervous system. So the complexity of this system is very high. This system in the biology, it consists of multiple layers. The first layer is a skin. Skin is responsible for removing pathogens in 80-90%. So this is a Next, we have physical barriers such like body temperature, pH, tears, and so on. Next, we have 2 layers which are generally the immune system. So those system is divided into 2 parts. We have innate non-specific immune system, the adaptive immune system. The innate immune system, this system we have when we born, and this system does not change during our life. The adaptive system, this system is learned during our whole life. And this adaptive system is used only when the skin, physiological barriers, and immune system not remove the pathogens from our body. The artificial immune system mainly focus on the last one, the adaptive immune system. This system will learn with life and will fight the infections. What is the most important in the human biological immune system? When we compare the number of own cells with the estimated number of different pathogens. The number of pathogens is 10 to 16, but the number of own cells is about 10 to 6. So the number of pathogens is bigger, much bigger than the number of the own cells. So, artificial immune system, sorry, not artificial, immune system able to recognize certain amount of things, but they mainly use only the information about ourselves. So to protect the body, we don't need an information about the pathogens. It is enough to have information about our own cells in general, because there is, of course, the memory and our organism remembers the pathogens. But in general, immune system do not require information about the pathogens to recognize. If we move this information to the cybersecurity, you can imagine the system that in which we do not have a tools, for example, in the snort, in the firewall, which recognize and patterns. It is enough to have information about our profile. And everything what do not belong to our profile will be treated as a network contacts, pathogens, and so on. Select cohorts. As I already said, immune system is a very complex system. It is focused on the discrimination between our cells. In the artificial immune system, we'll say that these cells are named both cell, and these pathogens are called immunes. Of course, these pathogens should be detected and eliminated from our body. And the key advantage of natural immune system is that they can detect also pathogens entities using only the information about our cells. The information only about our cells is sufficient to detect the pathogens. As a result, every organism has the unique protection system. So this is a difference when we move this information to the cybersecurity domain. When we use the standard antivirus system, intrusion detection system, we have the same database, we have the same signatures, we have the same rules in the firewall, almost. We have the same rules in the intrusion detection system. In the immune system, each body, each organism has unique action system. So it is not possible to download the database of type signatures. We need to learn about our environment when we exist. Okay, based on the information about the natural immune system, of course, natural immune system are very, very complex. I should show you only the main information about this system. Artificial immune system, of course, are inspired by the biological human immune system. They are adaptive, distributed, and self-organized. There's no central organization. There's no central item in the body which are responsible for fighting with the pathogens. Generally, each cell, each tissue can protect our body against the pathogens. Of course, the artificial immune system are able to detect different types of anomalies, pathogens. Those systems can also learn the patterns. They remember these patterns in the immune memory, and if the same pathogens will find in our body, then we can use the information from immune memory to give the good response to this. And of course, this system is very complex and can be used in the dynamic concept environments. Core principles of natural immune system. This system, as I already said, is responsible for discrimination between two classes: our cells, self, and pathogens, non-cells. They use the pattern recognition and learning. They have the memory of infections, and as I already said, this system is decentralized. So there's no one item, one element in our body which is responsible for protecting them. Inside the artificial immune system, there are developed a lot of algorithms. And those algorithms can be applied into different domains. Here, you can find the basic algorithms. We have negative selection algorithm. They are usually used for detecting anomalies, not only in cybersecurity, but are used in each domain where the classification into two classes it is enough. Generally, in the cybersecurity, it is enough to divide attack, not attack. If you would like to determine what kind of attack it was performed, then you can use, of course, another algorithm. But the basic classification can be used by negative selection algorithms. We have clonal selection algorithm, which is inspired by immune memory, immune network models, danger theory, dendritic cell algorithms, and so on. So a lot of algorithms which are developed in domain artificial immune system. Today, I will focus only on the first one, on the negative selection algorithms, different algorithms with some modification and so on. So, artificial immune system, which use the negative selection algorithm, should prevent the network or living organism. Depends if we focus on the living organism or the computer network. We should prevent our environment against the pathogens. It consists of many elements, cells, tissues, and other organs which work better to protect our body. But the main role plays the limbs. The lymphocytes, they can be divided into two groups. We have T cells and B cells. T cells, lymphocytes, are responsible for seeking the stuff. This is military intelligence. When the T cells find the pathogens, B cells are responsible for killing these pathogens and removing these pathogens from the when we move this information from real life to the cybersecurity, in the cybersecurity, we have generally two main approaches to detecting attacks, anomalies, and so on. We have signature-based system, and another option is anomaly detection. In the signature-based system, we can use the general rules for detecting the attacks. In the antivirus systems, we can download the signatures of viruses, and we can download such database with signatures and use in our system. When we use intrusion detection system, for example, SNOR, we can download the general rules which will protect our environment. So when we use the signature-based system, the all systems are protected in the similar way, because we use the same rules for antivirus, for snort, and so on. When we use the anomaly detection, we have in this case, each system has a unique protection system. So each system use the different rules. What is the most important in the anomaly detection approach? The most dangerous attacks are attacks. When we have no signature of such attack in our database. Until we update our database with the signatures, we are not protected. Such 0 days attack can be passed to our system. In anomaly detection system, even if a new attack, 0 day attack, appears, it will be different at our body. So this type of attack will be detected by our system. So this is a key, in my opinion, key option why we should use the anomaly detection system to protect our network, our computer system. The problem is between signature and anomaly detection approaches. Main problem is the complexity. Signature-based algorithms are they're much less computationally complex than anomaly detection. So detection using the signature-based algorithm, it's performed very fast. When we use anomaly detection, usually it takes much more time. I will talk about these problems later, but I think it's the connections with those two types of approaches can give the best results. We can use signature-based algorithms and anomaly-based, which and in this way we can connect to not connect, but more. Let's focus on the linear research algorithm. In this algorithm, when we have a universe, the set of possible connections, network connections, for example, when we have an information about, we get data and information about our own cells, our own network activities, which are normal, then the universe can be divided into two parts, self and non-self. And the conjunction of self and non-self is empty. Because we have to classify it into two classes. The connection or pathogen should be classified as self or as non-self. It cannot be self and non-self. So if you have only information about only our self cells, our normal network connections, we have to create a set of detectors based only on information about our which will cover the subspace in our universe, cover the whole subspace of non-self elements. So these detectors should be activated when they found the pathogen, when they found the network attack and so on. In the ideal world, if we have a universe cell, we can divide them into self and non-self. We have to, well, should be the different color. we should cover the nodes of space. And everything what is detected by the devices should be taken out of the sun networking part. But usually in real life, we do not have even the information about all our cells. So we can divide the cell into two parts, as seen and as unseen. And this part represents our cells, our network activities, which were not gathered yet. So in this case, when we have only information about as seen subset, our detectors could cover also even this subset as unseen. It is not good. This part represents our normal network activity. But in the real case, we can divide our universe into four subsets, not only as seen and as unseen, but when we try to cover the subspace N, we are not able to fulfill this part without any holes. And this part represents the holes. If the network attacks will be located in this subset, it means that this network attack will be not impacted by the So when we try to generate the detectors, we should try to minimize this. If we cover all the whole space of N, then we will have no holes, and all network attacks will be. Selection algorithms, we have two basic different approaches. We have B detectors and D detectors. It depends on the representation of data. If our data consists of binary strings, then we can use B detectors. If our data sets consist of real values, then we can use B detectors. Of course, the complexity of B detectors is much lower than B detectors. Because here we have a lot of multiplication and so on. In the B detectors and D detectors, we need to define affinity matrix. This affinity matrix or distance matrix will be used for checking how far is pathogen from the if the affinity matrix is low, then we can assume that this detector detects the. If the distance is, then these detectors, this detector will not recognize the. And in case of B detectors, we have here you can find only three distance matrix for affinity matrix. Having distance, R continuous bits matching rule or R chunks matching rule. When we use the detectors, usually use the congruence distance. Sometimes we can use Manhattan distance. The complexity of Manhattan distance is much lower than Euclidean distance. So when we need a fast detection or fast process of learning the system, then because in the Manhattan distance there is no multiplication. Generally, we can use the Minkowski norm. Inside the Minkowski norms, of course, there is a Manhattan event distance, because Minkowski norm it is a general rule for finity distance. Let's start with either. As I say, here all data are represented by the binary string. And for example, we have a self set. Our patterns are represented by 8-bit binary strings, L is equal to A. So, for example, we have a self set. We have 4 self samples. All the samples are 8-bit length. We need to generate the detectors, binary detectors, which will detect all the patterns except this set. How these detectors are in case of P detectors and D detectors, we generally use they are generated in the random way. So we generate a random binary strings, for example, this one, to check if the distance between this possible detector we calculate the distance with all the samples. If the distance is too small, then the detector is rejected. If the distance is high, then we can put this detector to the sets. In this way, we can build the sets of our detectors. Of course, we can use different matching rules, different affinity metrics, and so on. In this case, I use the matching rule. It works in this way that we have 8 bits. If we assume that R is equal to R, very continuous bits matching rule, R is free. So we check free bits. On each position, check if the pattern is the same. For example, in this case, those pattern and possible detector are the same because we found 3 continuous bits on the first and the 3 positions in the detector and in the so of course the value R must be less than the length of the binary binary. If you have a set of binary detectors, we have tested pattern, it's a network connection, for example, and we check if this pattern can be recognized by any of these detectors. Like you can see, in this position, we have 3 continuous the same bits, 1, 0, 1, even 4 bits, we have the same, but 3 bits in our case is enough. So the detector will detect the patterns, and we have anomaly. If we choose another tested pattern, in this case, none of these detectors will detect this. The distance between this pattern and all these detectors are big, so we can treat this string connection as a normal. So this is another approach. Now, this approach was used also for intrusion detection system. It was proposed by Hofmeier, the system called Mises, and as you can see, it's a very simple system, because here we can use only the strings with length 49 bits, very short binary strings. And what information were used. Source IP, destination IP, the flag. The flag means that it was connection to the server from server, and the service generated both now. As you can see, this is not enough information to detect most of the network attacks. Even it was used, even in this case, IP version 4. So destination IP even 32 bits. The source IP is represented only by 8 bits. So it assumes that source IP belongs to the class C of IP version 4. Why? We have only IP version 4, and why the source IP is such short value? Because binary representation in the binary representation we cannot use the strings which are longer than 15 bits. They are not for the longer representation. We are not able to generate the detector set because it takes too much time. It's not that those detectors are generated randomly, so it is difficult to generate such possible detectors and verify if this possible detector can be moved to the detector set or it cannot be used as a detector because it recognises kind of so binary representation this cannot be used for intrusion detection system because it's not possible to generate good detectors. Here we find the probability of generating detectors depending on the data length. And it was used only for 20 bits length patterns. And you can see that we cannot generate, it's not possible to generate two small binary detectors. Because, for example, if we have a string and it was r equal 1, then probably such position in the subset, we have also the values 0 and 1. So it is not possible to generate such detectors. Even if you have only 20 bits length binary strings, we can generate detectors starting with 6 bits up to 10 or 11. Shorter detectors are able to detect much more anomalies. If you have very long detectors similar to the value pair, then those detectors are too specific. They're able to recognize even a single colors. So we are interested to create the detector set which with the length with the lower length. In this case, for example, the detectors with the length 7, 8, much better than 11, because they can recognize much more patterns. Of course, if we have less number of detectors, then the recognition is performed faster than if we have a lot of detectors. Now, detectors, different approach. In this case, the symbols are represented by real valued detectors. And strange. The colors are not properly.
So when was that on the other slide too? It doesn't show gray for some reason.
So if you assume that this square or Python cube is a universe set, the self-samples are represented. Let's focus on the two-dimensional data sets. The universe is a square. Self-samples are represented by circles with radius, and the detectors are also represented. You have to trust me, these are the circles. So we put the self-samples into universal or universal set, and our goal is to fulfill this square by the V detectors. But V detectors cannot cover any of self-samples. If we do not cover the whole space of non-samples, we'll have some kind of holes. For example, here, if we meet the pattern related, for example, from this point is not covered by detectors. It is a hole, and this pattern will be treated as a normal behavior. The shape of the detectors depends on the distance affinity matrix. When we use the Euclidean distance, then in the two-dimensional space, detectors and self-samples will be represented as a surface. If we use the Manhattan distance matrix, then self-samples and the detectors will be represented as squares. But of course, we can use the other Minkowski norm, and then you can see here is Manhattan distance and Euclidean distance. But when we use the Minkowski norm, and especially when we use the fractional distance matrix, when this value is fractional, not the round number, we will have the different type of shape. So the shape of the self-samples and the detectors generally depends on the distance affinity matrix which is used in this system. Here there's a basic algorithm for generating V detectors. Those detectors, of course, are I will move to the previous slide. How the detectors are created? We randomly select the point in the universe. We calculate the nearest distance to the self-sample. Then we can create a detector with the center in this randomly selected one. As you can believe, this is the algorithm for generating the detectors. Of course, those algorithms were tested on various types of data sets which consist of network patterns, and also for Iris database, data set, chemical merge data sets. So in many cases where the classification into two classes, it is enough. Of course, take the up 1999 kilo plus this data set represents the and this is results for the Iris data sets, and when we have the estimated coverage of about 99%, as you can see, almost all Iris flowers were correctly classified. When we use the estimated coverage on 99.99%, all all flowers were properly. See, all this is the estimated cost because we have to find the moment when we could stop detecting the detectors. 99% means that we have 99 continuous changes to. In this case, we try to generate the detectors 100 times, 99 times. All these tries failed, then we can assume that you have a estimated coverage around 99%. So in this case, we need to get about to generate the detector which failed, and then we can assume that estimated coverage is on the level of 99.9. Here the result for KDD tab with the network connections data set. Generally, it was not possible to work on the whole data set because this data set was very, very big. So millions of elements are inside this obligatory inside this data set. So I divided this data set into protocols and made the test for ICP protocol, TCP, and so on. Because it is easy, when you have a connection, it is easy to recognize type of the connection. It is better to create detectors which are specific for some protocols than create the general. So I told you about the B detectors and D detectors, and my proposition was to create a B model. So in this model, I propose to use both type of detectors. Because the B detectors are faster than D detectors, I propose to divide the classification process into two phases. In the first phase, the patterns are classified by B detectors, fast B detectors, and if the B detectors do not recognize this pattern, then we can use the B detectors which are computationally more complex. Of course, in this case, the classification process is longer in comparison to the case when we use only B detectors or B detectors. But using this model, we can detect much more anomalies. Of course, when we use both type of the detectors, because both detectors are represented by different so detectors are binary string, revalued vectors. To create such model, we have to transform the detectors in the real groups. And for example, this is a representation of the of course, during the creating the detector set, we take into consideration the previously created B detectors. So this hypercube universum is fulfilled by B detectors and B detectors, and B detectors cannot cover the B detectors because it is not needed to cover the space by B detectors and B detectors. And these are some results for diabetes and handwritten words. And as you can see, the straight line is a B detector algorithm. So you can see that, for example, the detector detect the unactive words on the level 83%. But when we use the also binaries, detectors additionally, we can achieve about 96% accuracy. So when you compare these values, you can see that there's a big difference between using the single type of detectors and when we use both type of and the last one, multiplication graph theory. Graph theory was developed by Polish mathematics, Zdzisław Pawlak, in 1980s. And in this theory, you can divide the all patterns not into the two classes, not non-self, self and non-self, but we can create another third class, possible self or possible non-self. We don't know. It was an attack or it was an interaction. You probably know that it is difficult to recognize the network attacks which are very similar to the network connections, to the normal network connections. If this distance is too short, then such pathogens, such network attacks can be passed by our intrusion detection system. So in this case, we create the third class, possible, yes, or possible self or possible non-self, and in this algorithm, when we because this is our self-set or universe, and the green area, we are sure that this is a self. Green, red area maybe self, maybe self, maybe no self, and here we have no self, non-self. So in the between green and red lines, we are not sure attacks or not attacks. And in this case, negative selection algorithms can be used as a second process. We try to divide into self and non-self, but in some cases we are not able to determine it was self or non-self. And then such suspicious patterns can be, for example, classified by another kind of algorithms, for example, statistical or other types. So here we can treat negative selection algorithm as some kind of preconception. We can probably the most of such patterns can be classified, but in some cases we are not sure. So in this case, we use the big detectors. We can use all the big detectors are represented not only by the center and the radius, but such tolerant big detectors are represented by tolerance. Low approximation and high approximation. Inside this B detector, we know that is between the radius in this area, we are not sure. And those patterns can be classified as by another. Of course, in this case, the problem with the classification is that sometimes we have some outliers. We have some data which are which can which are not used classification for if they are self or non-self. In this case, some outliers can be covered by such tolerant detectors, and such outliers can be classified by another type of another state. case. So in the tolerant detector, we have three classes, not two classes. We have non-self, self, and we have the third class, uncertain, which we don't know. They are for non-self, and then such samples should be classified by another type of algorithm. So results of the detectors, tolerant detector of the detector algorithm, of course, it was tested on a lot of type of data sets, but here you can find that this is from Kiosk and Kinetic 1999, which consists, as I said, network connections, and those data sets are used for testing the network attacks algorithms. And you can see that the detection rate with this is parameter key, it can be increased from the basic algorithm on the level 12%, even up to 93%. Of course, others patterns can be recognized additionally by another algorithm. So the detection rate can be even higher. This is some conclusions that I already told you about is that if any pattern is not recognized correctly by the tolerant detector, then they can be classified by another algorithm to increase the detection rate, and of course minimize the false alarm rate, which are not. We should be as low as possible. False alarm rate means that the normal connections are recognized by normal connections are recognized as a network. That's all. Thank you for the question. Thank you for the question.
I have a question. When you suggested the easy detector, my question is, does it consume a lot of CPU and RAM? Does it require a very more potent computer for its to run? Since
Yes, you're right, but it consumes the CPU only in the learning stage, not in the classification. The learning stage is, of course, much longer because you have to generate B detectors and B detectors. But we assume that B detectors do not cover the space covered by B detectors. So during the classification, we can use at the first stage very fast B detectors, and then we can use B detectors which are more complex, use the multiplication, a lot of multiplication, and so on. The detection, the creating of detector set is really longer, much longer in comparison to V detectors and B detectors. But we can make such process, for example, in the idle time of CPU.
okay.
And on the test that you have performed, what was the percentage of findings used by that the B detector have found on the performance? Because it is much quicker, okay?
Yes,
So
yes.
it detects if the anomaly is detected firstly, well, we will say the CPU and computational process for the V detectors. So normally, what is the percentage of detection of the first anomaly? Do you have that kind of value?
I mean, probably there's no such.
It's just a question.
Here, there's a difference.
Okay.
This is the only when you use the V detector. So the detection rate is under, for example, 3%. But when we use also B detectors, the detection rate increased more than 96%. So of course for this. Yes.
Great. Here's a question regarding B detectors. You mentioned that B detectors typically operate with 50-bit strings in a real world use cases.
Yes.
So how many dimensions do B detectors usually operate with?
No, it's a difficult question, but I found that some mathematicians say that because in the B detectors we usually use the Euclidean distance to calculate the distance. Some mathematician says that Euclidean distance is good for 7 bits up to 200, 250. For higher binary string, longer binary string, Euclidean distance cannot be used. Of course, we can use another distance matrix, Hamming distance, sinus matrix. Of course, we can use for calculating the distance and so on.
But B detectors themselves, there are how many dimensions?
There's no limitation, but during the learning phase, we have to fulfill the universe. So if you have a hypercube in 3 dimensions, it is easy to fulfill this space by B detectors. If you have 45, 50, 100 dimensions, it takes much more time to fulfill. And it is difficult. We need to use the good algorithm for selecting the random place as a center of B detector, because for creating a D detectors based on the randomly selected centers of the D detector. We have to randomly select the center, relate all the distances to the self samples, and then the such B detector is created. So generally, we should use algorithms which will decrease number of dimensions. If the number of dimensions decreases, then the detection rate will be higher, and of course the detection phase and the learning phase will be much faster than in case when we have a lot of dimensions.
Another one. So my question was like, since these artificial immune systems are based on natural immune systems, we have cases like cancer where normally cancer has its own DNA, and that's why our immune system gets into attack it. So what about situations like that when we have a pathogen that's so similar to a system that what happens then? What happens when the pathogen is so similar that it's probably very difficult to recognize or separate?
If the pathogens are similar to our own cells, then we can classify cancers. So this is a problem.
So there's no.
If we do not fulfill the subspace non-self without the holes, so there are possible that some patterns which are attacks, which are pathogens, can be wrongly classified as a cell. So this is a key problem: how to fulfill the universe, not the universe space, the part of the universe space which represent the non-selves. So those algorithms are necessary, are computational complex. They maybe should be used as a some kind of reprocessing and for detecting new type. We can imagine the system that all the connections on the firewall and the intrusion detection system are classified by signature based, which are fast. algorithms. For example, this connection will be passed to the firewall, but in the next stage, system will work with the anomaly detection. And maybe with some delay, but such attack will be detected, and then we can perform any security options and, for example, block such connection with some delay, but we are able to detect such new type of attacks.
Or even create new secrets.
Yes.
Yes.
Folding at home is distributed computing initiative for getting useful proteins. Subscribing users can provide some of their own computer resources to help from new prior diseases. Are there any such initiatives for detecting or detectors for artificial immune systems? Folding at home is a computer initiative. So subscribing users to Folding at Home that get some of their own finding ways that proteins can be useful. This helps in prion disease investigation. But similar initiatives in generating detectors or
No,
yeah.
it's not possible because in this approach, every system has a unique protection system. It is not possible to create general databases which can be downloaded from any resource to our local computer. In this case, we have to create some kind of learning phase. During this learning phase, we are learning about ourselves, about our normal connection. Then we stop learning. Based on this gathered information, we build the detectors, and since this time, every connection which is recognized by these detectors will be treated as a normal connection. Yes?
Yes, going to ask related to our first question. So it's being created by the person. Imagine it was a viral vaccine where it's injected into the computer and it's on the immune system adapts to the new attack. I think it's signature based. Then I sure.
Motivated students.
I will think about
And we have the next session. So
Białystok. Nie chciałem ci Białystok.
questions.
Yeah, more
I was going to ask. I think this example are based on more academia. I'm thinking if there is anything that's more non-academia where artificial immune systems are being used in
Maybe industry.
yeah, like industry and stuff like that.
I know that it's possible. I try to adopt this algorithm in the snore. It's possible to apply such needs. But industry, I don't care about such things.
Is there a reason
Some
why?
scientific, it's not.
Is there a reason? It's just because it's still being investigated.
Because probably first reason, it is easier to download, for example, signatures of viruses, than create unique system for each computer, for each lab. The knowledge of such IT administrator should be higher than the standard positions.
Okay.
More questions? So, thank you very much. Yeah. it was very interesting. It's a different approach. It's new for me. It's a very nice approach, and I think I will grab some papers and try to understand a little bit more about the session, and it can be applied in other situations.
Like we create a paper. Okay. The students.
Main use that will be part of our curriculum.
When you were talking about the TCP and UDP, I became interested and I thought really there was some kind of applications in English, especially related to networking, since there's nothing. Because it's very interesting, and as students, those of second year can verify. For me, we have a module that's called cryptography and network security. That's it, and network security. We try to always not teach access to go and investigate ways to kind of like protect our system or network. Find it very interesting, and I feel like it should be implemented. This.
You can try. You can try here the system which is protected by immune system.
Yeah. The only one.
The university is before the industry. It should be tested in the.
Yes, of course. But since you refer to SNOT, maybe it can be
Yes.
it can be applied to SNOT.
Yes.
So next time we have a project.
Essentially, there can be centralized database for you, but surely there's like a human base, like thing that's common to all things. Any ways to build such a database that can then be specialized for.
Probably can be. There are some organizations which are very similar. And for those organizations, we can create the general detectors, for example, for universities. Right? We know that students use use the some kind of websites, use the connection. We can create some general detectors which can be used in many places. But we need to find such organizations which are very similar regarding the type of network connections. But it cannot be used probably for the whole world because we are different. We have different organisms. We have our immune system are completely different. We have different innate system, and we have a different adaptive system because we live in the different environments.
I think we should go before starting. Rather than you without questions. And one more questions. More questions? Very well. Thank you very much, President. Thank you for coming here and giving this beautiful talk. And I think now we should go and eat.
It's very nice to meet you, and I will invite you to Białystok, Poland.
Yes, we can.
Very next visit.
Yeah, next visit to
Especially in the winter semester, minus 10, minus 20. Yes.
we'll get some answers.
You were in the Białystok in the summer?
Thank you very much.
These are the some sweets from Poland. This is the dog, means that milk from the bird. It's not from the bird.
No one is. You can like this dizer. Anyway, to those watching at home from YouTube and Instagram, thank you for joining us through YouTube and through our Instagram. We're very happy that you guys took your time to kind of join us and to listen to Dr. Andrzej. We'll be back at 2 o'clock, so stay tuned and thank you very much.